Okay, so in this particular section, we're going to look at testing a function or an equation for symmetry. We're going to do it with the x-axis, the y-axis, the origin, and y equals x. We're also going to look at whether a function is even or odd, being able to test for that. And we're going to be supplying some different graphs of functions using some transformation rules, okay? All right, so example 1, let's go over the symmetry rules first. Okay, and I've color-coded these. So let's say I'm just working with a standard point whose x-coordinate is positive x, y-coordinate is positive y. That puts me in quadrant 1. If I reflect that over the x-axis, that's going to put me right about there. And the coordinates of that would be x negative y, right? X-coordinate would remain the same. Y-coordinate would have to change the sign. Okay, if I reflect over the y-axis, that original point of xy ends up over there. And now the x-coordinate becomes negative and the y remains the same. Okay, next one you might be a little less familiar with. If I reflect something over the origin, recall what that's going to do is change the signs on both coordinates. Okay, so we had xy, it's going to become negative x, negative y, and it's going to end up over here in quadrant 3. And then this last symmetry rule is what we talked about yesterday with the inverse functions. If I reflect over y equals x, which is this line, what happens to the coordinates of xy? Becomes yx, right? Comes over here and is now yx. Very good. Okay, so let's test the equation y equals x squared minus 3 for all 4 types of symmetry. And again, let's color code these. If I want to test for the x-axis, I know the point xy should turn into x negative y, right? So in this original equation, I'm going to replace the y with a negative y and simplify it to see if the result is the same as the original. Okay? Well, in this case, that's not going to happen. I'm going to end up with y equals negative x squared plus 3. So that means that the point of x negative y is not producing the same equation, the same result as the original y equals x squared minus 3 is. So that means there's no symmetry here with the y or with the x-axis. Okay, what about the y-axis? So here we would replace x with a negative x, but we would leave y alone. So this would equal, it would be y equals negative x raised to the second power minus 3. Notice the use of parentheses there. That's important because it shows that the negative is getting squared. And look what I end up with. The same equation that I began with, right? So I will say, yes, we do have symmetry with the y-axis. You're basically saying that negative x is producing the same result as positive x would. Okay. All right, what about the origin? Now you're going to substitute a negative x and a negative y in. Well, that is going to leave me with the same thing I got over in blue. Y equals negative x squared plus 3. That is not the same as the original, so no symmetry here. All All right, and lastly, y equals x. Okay, so here we switch the x and the y. We make it x equals y squared minus 3. That's x plus 3 equals y squared, or y equals plus or minus the square root of x plus 3. Clearly not the same as the original equation, so no symmetry here. So this original equation of y equals x squared minus 3 only has symmetry with the y-axis. You might have been able to reason that out from the get-go. You're familiar with that graph. It's just a parabola that's shifted from the origin 3 units down. It's doing this. Okay, clearly that has symmetry with the y-axis, right? All right, example 2, we've got a couple other equations to do the same thing with. X equals y squared minus 3. Let's do x-axis first. And again, the rule is xy becomes x negative y. So replace y with a negative y. Use parentheses here. And I result in the original equation. So I'm going to say, yes, we have symmetry here. Okay, y-axis, supposed to be negative x, y is the result of that. Well, negative x would equal positive y squared minus 3. That's x equals negative y squared plus 3. Not the same as the original. No symmetry with the y-axis. How about the origin? Negative x, negative y should be the result if you reflect over it. Substitute negative x in for x. Substitute negative y in for y. Negative x is going to equal y squared minus 3. Or x equals negative y squared plus 3. Not the same as the original. No symmetry with the origin. And lastly, with y equals x, the point should turn into yx. So I substitute a y in for the x. I substitute an x in for the y. And there's no way that's going to simplify back to the original, right? So no symmetry there. Okay. All right, now, did you notice the original equation, x equals y squared minus 3? That's just the inverse of the first equation we worked with on the previous example, right? I just switched the x and the y. Okay, so we saw that this graph was a parabola that opens up. This graph would be that same graph, but rotated to open to the right, okay? And therefore, it gives you the symmetry with the x-axis now, okay? All right, the last equation we're working with, x squared plus y squared equals 1. That's an equation of a circle, and that's not just any circle, that's the unit circle, isn't it, from trigonometry? Okay, it's got a radius of 1 centered at the origin. Picture that, radius of 1 centered at the origin. When we go through all these 4 tests, what should be the conclusion for all of them? Yeah, they all 4 should be true, right? So let's just verify that. X-axis. Okay, I'm going to make it, that's when x stays the same, but y becomes negative. All right, so that'll look like x squared plus negative y squared is equal to 1. That's x squared plus y squared equals 1. Yes, symmetry. Okay, y-axis, negative x raised to the second power plus positive y raised to the second equals 1. That's still going to be x squared plus y squared equals 1. Symmetry there also. Origin, we're going to see the same thing. If I replace x with negative x, y with negative y, I'm still going to get x squared plus y squared to equal 1. And lastly, y equals x. Well, if I switch the x and the y, commutative property says that's the same as x squared plus y squared equals 1, yes? So as we reason out at the beginning, just by visualizing the graph, we do have symmetry in all 4 respects. All right, example 3. Function is said to be even if f of negative x equals f of x and has symmetry with the y-axis. Okay, so symmetry with the y-axis, we said xy turns into negative xy, right? So what that's stating is evaluating with positive x produces the same y value as if I evaluated with negative x. And that's what this function notation is showing. If I evaluate the function of negative x, I'm getting the same y as if I evaluated with positive x. They're equivalent. Okay? To be odd, you have to have symmetry with the origin. Okay? And that means xy is becoming negative x, negative y, right? So in terms of the function notation, evaluating the function with negative x should produce the opposite of whatever the function is evaluated at x. Okay? F of negative x equals the negative of f of x. So let's classify the following below. All right? F of x there, I'm going to evaluate it with a negative x. And that's going to result in negative x cubed plus 4x, which is the opposite of the original function. That's the negative of the original f of x, right? So this is an odd function. G of x, if I evaluate it with a negative x, look what happens. I just get x squared minus 3, which is the same as the original. That means we're even. And h of negative x is going to be negative x to the 5th minus 7, which doesn't equal h of x. Those are not equivalent. And it's also not equal to the negative of the h of x because the 7 is still negative. So therefore, this function is neither even nor odd.